Hi, this is Sholey Physics episode on drag. Today you're going to learn about terminal velocity of a falling object that's under the influence of a significant air resistance. This is the point where air resistance is no longer negligible. We're also going to find the motion functions, motion equations that a falling object is going to have. So what is its acceleration curve going to look like, velocity, and displacement as it falls. So we're going to start out talking about objects that are falling. Let's take a parachuter jumping out of an airplane. The first thing that's obviously going to take hold is the weight of the person, the gravity pulling straight down. And initially, at the beginning of the jump, when time is 0, acceleration is the full amount, 9.8 meters per second squared. And that's because there's no drag yet. Drag is dependent on velocity. If you ever roll down your window in a car, you stick your hand out in a safe kind of manner, you're going to notice some air pushing against your hand, but when the car comes to a stop, then there's no longer any air resistance, there's no longer drag. And as you get faster and faster and faster, you feel that backward push increase. So velocity is just, it's very observable that it affects drag. So with 0 velocity, when the person just jumps out, initial velocity is 0 here, there's going to be no drag at all. All right, a little short time later, the fall has progressed a bit, so t is greater than 0 here. What's going to happen now? Well, the weight will be the same weight. And let's remember that weight is mg. Go ahead and label that, mass times 9.8 here on Earth. But there's going to be a little bit of drag. The parachuter will have increased his or her speed, and we're going to pick up some velocity. So there's now going to be drag. And like I was just indicating, that's proportional to v, some kind of v value. Now this actually could be a v squared or v. It turns out that objects that are falling and moving rather quickly, it's more of a v squared proportionality. But it can also be, especially the lower speeds, be proportional to v. We're going to probably use v in this presentation here today. So at this point, with a little bit of drag, then there's no longer only the acceleration due to gravity acting here. There's an opposing force. So acceleration is going to be less than 9.8 at this moment. And the velocity is going to be increasing. Velocity is increasing, speeding up here. All right. Now a long time later, where t is much greater than 0. So a long time has passed. What's going to happen? Well, as you might see, what's progressing here, the weight remains the same weight, but drag is going to increase until it reaches the same magnitude as the weight. And why does it stop there? Well, because when weight is equal to drag, what's the acceleration? 0. That means the change in velocity is going to stop. It's going to stop changing velocity. So velocity becomes a constant at this point. And that's an important note. The velocity is constant. It doesn't get any faster. And this is what's called a terminal velocity. Terminal like ending. Like a train terminal is where the train comes and ends. Look what happens to this velocity. It starts up at 0, it's increasing, but it becomes constant. So it's increasing until it becomes constant. It's approaching a maximum velocity, and that's called the terminal velocity for objects in free fall. And this is where the weight is equal to the drag force. So we can actually calculate that terminal velocity working right off that force diagram. We have a force diagram set up. In problem-solving process, we're going to apply Newton's second law. And downward, we'll just call that downward is positive because, objects are falling downward here. So I'm just going to call that Fg equals mg. So we're going to have a Fg minus the drag force equals mass times acceleration. But at this moment, the acceleration is 0. So we see that the weight is equal to the drag at this point. Okay, that's what I described just a moment ago. So when weight's equal to drag, what else can we figure from this? This isn't very interesting. We want to know a little bit more about this terminal velocity fellow. So we got to start thinking about what drag is. I mentioned earlier that drag is proportional to v, but drag, if it's proportional to v, why don't we put a proportionality constant in front? We'll call it k, and v bringing us to what a possible formula for drag is. Now, when you apply this experimentally, when you drop a bunch of objects, you can actually figure out what k is for a particular object falling in a particular fluid substance. So what goes into k value here? I'll talk a little bit about this, this drag force. I'll bring it down here. What goes into the k is something called the drag coefficient, and that has to deal with the shape of the object. All right, so is it a spherical shape? Is a circular shape, which could be different. Spherical might allow air to move more smoothly over it, whereas a circular object would, like a cylinder dropping, has a flat surface. Is it square? Is it streamlined? Is it a raindrop kind of a shape? So a lot of things can go into the drag coefficient. What else might affect this k value is the surface area, the surface that's facing that drop. So the surface has a shape, but it also has a size to it. So take a small styrofoam ball compared to like a really large styrofoam ball. Maybe the mass isn't a whole lot different, but the size is. So the surface area that's facing that oncoming air, that's going to have an effect. What else might be in here? Oh, it's moving through air, or it could be actually moving through a different density of air. It could be moving through water even. Do you ever consider that an object sinking down to the bottom of the ocean is experiencing drag or water resistance? Okay, so there's the fluid density and properties. I'll put that density and properties. Is it viscous? Is it difficult to move around? Is it what are those fluid properties? So those are just some of the aspects that go into this k value. All right. So we got a little bit of a formula for drag. And like I said before, this can be kind of a v squared type of proportionality, but at a lot of points along the dropping path, it does turn out to be that if you consider a very gradual parabola, like a v squared type of proportionality, sections of it can be rather linear. Like if you just look at this first part here, it's approximately linear. There's not a whole lot of curve to this relationship here. So for the purposes of this presentation, we're going to use just a v, because if we use v squared, then the math later on is going to be a bit more complicated. So we're going to keep it to v. All right, and so we're ready to get more of a relationship for what is terminal velocity in terms of some other physical constants and properties of this drop. So let's substitute mg for weight and kv for drag. Now in this particular instance, it's reached, this velocity is a terminal velocity, so I'm going to call it v capital T, terminal velocity. So this v is the terminal velocity where the acceleration is 0, where the drag is equal to the weight. Now if we solve for vt, and that vt is going to be equal to mg divided by k, the weight divided by that coefficient in the front there. Well, the drag coefficient, surface area, the fluid properties, properties and density. As you see, this k value, it in itself is not just a coefficient, because this is a force over here in newtons, the velocity is in meters per second. So this k value does have units. So it's not the coefficient. Sometimes I misspeak and I call it the drag coefficient, but it is a constant out here for this scenario. So there's our terminal velocity, and I'm going to just box that in so we remember it. We're going to come back to it a little bit later. My next question is, what is the acceleration function, the velocity function, so the function of time, and the displacement function, we'll call it y of t, what are these going to look like? What are these functions going to be? Are they going to be quadratic, going to be linear, or some other kind of creature? Now think about this. What's unique to this scenario is that there is acceleration happening, but we also have a drag force that's dependent on velocity. So when we start thinking about Newton's second law, this F equals ma, and the fact that drag changes while weight stays the same, what's going to happen between the start of the jump and a long time later? What's that transition going to look like? Not necessarily just later on when acceleration is 0, but leading up to that. So what we're going to have here, because drag changes as a function of velocity, that means the acceleration changes also. This makes a unique kind of situation. So what will that acceleration function possibly look like? Let's start to try to figure it out. And this is good. Like if you're given a question, and which of these equations represents the acceleration of a falling object under the influence of drag, you should be able to look at it and think about the properties. So what does the acceleration start at? Let's look. We already figured the acceleration is going to begin at 9.8 when there's no drag. It's going to decrease, and it's going to, it says a long time later, we don't really know how long, it's going to approach 0. It's not going to pass 0. This object isn't going to be accelerated, it's not going to be moving in the upward direction. It's always moving downward. The velocity is always down. So it's approaching 0. So we're going to start at 9.8. That's where it should start, and it should decrease, but it's not going to decrease and go past the 0 line. It's not going to become a negative acceleration here, because that drag never becomes greater than the weight. Unless you do change your shape and deploy that parachute, then there's going to be a momentary negative acceleration as you slow a bit, as the larger shape has a lesser terminal velocity than if you're just free falling without a parachute. So it's not going to pass 0 if you're just going to approach 0. So we don't want to have a straight line that passes that. We're going to start 9.8 and dip down but approach 0. Okay, so that's what that acceleration graph should look like. Approaching 0, start at 9.8. What about the velocity time graph? Let's draw one of those, sketch one of those. Going off the screen a little bit here. Velocity time graph. All right. Well, the velocities, where do they start? They're starting at 0. We're just jumping out of the airplane. They're going to be increasing, but they're increasing and become constant. So just like the acceleration approaches 0, our velocity is going to increase but approach a constant. So it starts at 0 and it's going to increase but approach a constant value, a constant velocity. And we'll call that point right there VT. And just recall that VT depends on the mass and the K value, the weight and the K. And just to think about that property, the greater the weight, the greater the terminal velocity. So it's like if I just drop a sheet of paper, it floats down, rather slowly. If I put a rock on it, and if the paper shape stays about the same, then it'll just fall almost straight down like a rock. Okay, so the greater the weight, the greater the speed that it can pick up before it becomes a terminal velocity. And also the greater the K value, the lesser the velocity. All right, so if there's more surface area, if there's a more dense fluid, that's going to decrease the terminal velocity. All right, so just thinking about how that works there. All right, so like if we do have different objects, how might that change these two shapes? Well, how about a sheet of paper? A sheet of paper approaches its terminal velocity rather quickly. So a sheet of paper dropping may have a acceleration that approaches 0 more quickly. It'll have a lesser terminal velocity, but it'll approach it rather quickly. So this might be a sheet of paper down here. This would be a sheet of paper acceleration. How about a rock? A rock would have a 9.8 for a rather long period of time, and it would take a long time in the drop to approach 0. And likewise, a rock might go up a lot higher in its terminal velocity and take a lot longer to approach zero. There's a rock. That's just to give a feel for the different possible shapes of these curves, but these are just sketches. I'm going to keep it straightforward, so keep those in comparison there. And finally, what about a displacement time graph? I'm going to use y of t here. What do displacements look like? Well, we're starting out at the top at 0, and we're going to go down towards the bottom. But there's nothing about displacement we've really talked about here. However, displacement time graph, its slope is a velocity. So we should start out with 0 displacement. But since the velocity is increasing here in the middle, we should have a curve. Just like if there's no drag, the displacement function is a parabola, is parabolic. But this one is going to end up with a constant velocity. So this curve is going to turn from a curve into a straight line, into a diagonal line, denoting the slope is remaining constant. Therefore, the velocities remain constant. So this function is going to be a parabola that transitions into a straight line. All right, well, this is showing like a little constant section, constant slope here. If you've been watching some Trolley physics and you watched and observed the drag, what a drag lab, you might remember that this was part of the lab procedure to extract a velocity, a terminal velocity from the data. I have a segment from that, a piece of data here I'm going to pull up. So this is data from that lab. This is the 7 filters data. And what I did in the lab procedure is I highlighted just this section down here. And this part, the velocity time graph, wasn't really observable then, but I highlighted this section. If you look at it, it's a constant slope. And in the beginning, this is more of a curved slope. So I was really looking for the terminal velocity in that lab, so I ignored this initial part. But you see that that curve, it starts out as a curve and it transitions to a constant. Now this view is opposite. In the lab, I had a positive direction being up, and we're talking about a positive direction being down. So just imagine these curves flipped, and we'd start out with an upward curve transitioning to an upward constant slope, and that's what my y of t graph looks like down there in the bottom right corner. It's a curve that transitions to a constant slope going up. It's in the opposite direction of data here. But also look at the velocity time graph. Might look a little funky. This data was not, velocity data was not collected, but this graph, what graphical analysis does from Vernier, is it just kind of extrapolates what the velocity curve might look like just by looking at the small changes in velocity. So this messy stuff down here is from a funny couple errant data points. You can see there's a little bump here. So the data wasn't exactly right along a line, so it got a little funky looking here with the graphical analysis. But with the velocity, you do see sort of a straight line here in the beginning. It's not really a curve to begin with. The data is kind of straight. So what this is showing is a negative acceleration. The object is getting faster in the negative direction. Of course, remember, negative direction is down here. So it's getting faster in the down direction to begin with. But what happens later on? If we look at this segment later on, do you see how the slope decreases? And it becomes, much later on, it becomes more of a constant. It's almost a velocity that is horizontal down here at the bottom. So this is what we're talking about. The velocity is changing initially quite a bit, but it becomes more of a constant towards the end. That's what we have back here in this, sorry, let me switch back on my other screen. That's what we have down here. It's changing quite a bit in the beginning, but it becomes a constant. All right, so can we actually come up with functions for these graphs? And what we're going to do for that, to get that, what is a of t, what is v of t, and y of t, we're starting from the beginning. We're not just looking at the terminal velocity, we're starting from the beginning. So let's start from this point here. but plugging in an a not equal to 0. We're not just looking at the end where we know the acceleration is 0, but the whole entire time. So we had weight going down minus drag going up equals ma, straight from Newton's second law. It's a great place to start. Substitute in our knowns, our expressions for weight, and kV's expression for drag. This is our starting point. mg minus kV equals ma. Now it looks sort of innocent, doesn't look very complicated. However, dun, 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 we have a v and an a, and these two are related. You see, the acceleration changes the velocity, and the velocity will then, because it's changed, change the rate of acceleration. They're intertwined. They're mixed up together. And the way you can really make this more evident is recalling that instantaneous acceleration is the rate of change of velocity at any given instant. So now if we substitute that in there, we get a differential equation, diffeq, if you ever heard that term, mdv dt. And here we see the velocity, but also a rate of change in velocity. So now, this is the key element. This is the difficult part, but with practice, it becomes part of you. And I do urge you to practice this. Once I'm done with this, practice it yourself. I'll get more into that later. All right, can we divide an m out? No, there's not an m here, so can't really simplify this a whole lot. But what we're going to do is we're going to try to get this to a point where we can integrate. Now, if you're thinking, oh, if I multiply both sides by dt, then I could just throw an integration sign on the front and be, those will cancel over there, and be ready to go. Except this v would have to be on the same side of the expression as the dv before we do all that. But this is where we're heading here. We're going to try to set up an expression that can be integrated as easily as possible. So this is not correct. We need before we integrate, we need to get these dv's and the v on the same side of the expression. So somehow I need to move this over and get a dt with a bunch of other stuff on the other side, just to set it up. But before we do that, I just want to start by dividing both sides by negative k. And the reason is, looking ahead, when we integrate, it's better to have, it's a little bit cleaner, to have no coefficients in front of our changing variable, in front of our variable. Okay, so we're going to integrate in terms of velocity. So if we remove this coefficient, it's going to be a little bit cleaner. So I'm going to start by dividing both sides by negative k. I'll just pick a different color so the eyeball can pick out the algebra a little bit better. All right. So when we do that, we're going to end up with a negative mg over k from dividing this term. When we divide this term, we're going to have a plus v. That's the purpose of dividing by negative k. And over here, we're going to have a negative m over k dv dt. Okay, it looks like I unsimplified it a little bit. It looks like, oh, there's now an m over k in two terms. What's up with that? But I don't know if you recognize this little term over here, and if you don't, just take a look back. mg over k is the terminal velocity. Wow. So terminal velocity becomes a constant towards the end of this fall. Just going to jot that up there as a memory. Vt equals mg over the constant k. So mg over k is Vt. I'm going to substitute a negative terminal velocity in here to see that, look, we're adding a constant along with our variable. This side of the expression is in terms of meters per second. This is a velocity. So I got negative m over k dv dt on this side. And just rearrange this to make it look a little prettier, v minus vt. And we're never going to forget our negatives and such. All right, now I'm going to do a couple things here. We want to get this to a place where we can integrate this expression. So I can't really multiply both sides by dt and just go with that. Remember we need this velocity over with the dv. So if we take this whole creature here, I guess I'll do this in parts. First, let me go ahead and multiply by dt. And along with that, why don't we multiply by negative k over m. So negative k over m dt on both sides. There we go. The reason is I'm going to try to cancel out this coefficient on the front here, called a coefficient because these are constants, and bring the dt to the other side. When we do that, we're going to have a v minus vt, negative k over m dt equals, the only thing that's left, the k over m's will cancel, the negative will cancel out there, and dt's are going to cancel here. So we're going to just be left with dv on this side. But now we can divide both sides by this creature, v minus vt. And hopefully you're seeing why I'm going through all these hoops. Now we're going to have all the v's on one side. That cancels out over there. And let's start with this, dv over v minus vt. Our terminal velocity is a constant, equals, the only thing that's left on this side is negative k over m dt. And this is an expression that we're ready to integrate. All right, every v is on this side, and here's a constant with a dt. So we can drop our integration sign. We can sum up all those little pieces of area, in essence, or summing up the change. And we also need some bounds, what are we summing up from and to? So this is going to be a definite integral. We're going to start with a time of 0 and increase it to some arbitrary time t later on. This is to give us a v of t function, what's velocity as a function of time. So likewise, we're going to just jump out of the airplane. The initial velocity is 0. This could be a v naught if you want to make it like that, but it's just going to make our result a little more complicated. Let's not do that. And it's going to increase to some arbitrary velocity v that's a function of time t. So this is the hoops we were just jumping through. Algebraically, I'm just moving some things around to set up the integral. We need the v's on one side and everything else on the other, along with the t. I also got rid of that coefficient. The reason, hopefully you might be able to see it now, if you've taken calculus before, well, the reason I bring that up is some of my students are in calculus now, and you're probably just going through derivatives and such. So you've done things like the power rule. Maybe you talked about e to the power of, or natural logs, but that's probably coming up later. But if you've taken calculus before, you might notice that this is of the form like a dx over x. Okay, if you ever integrate that, it's equal to a natural log of x plus c. Now if you just take the indefinite integral. Another way to look at this is x to the negative 1. If you've done some starting power rule integration, you'll notice that, you'll remember that power rule works where n doesn't equal negative 1. So that's where this natural log feature comes up. That is the integral table result of 1 over x dx. So that's the form we have here, and that's why I was getting rid of that coefficient in front, because we will have to use a substitution rule along with the natural log. And if you're just taking calculus now and you haven't gotten an integration, you'll definitely want to review this video later on. Just mark it as a look at later, study before the final, before the AP test comes up. Okay, but we are going to apply a substitution rule. So we substitute v minus terminal velocity. All right, this is our u substitution, and we're also going to need to know what dv is equal to. So if u is equal to that, we're going to substitute a u in here. We're also going to need to know what dv is equal to. So we take the derivative of this expression on this side is du, and derivative of this expression is derivative of v is dv, and derivative of a constant is 0. There's no change in a constant. So it's just du is equal to dv. Now I can substitute, and we'll see why we're doing this if you haven't done this substitution rule yet. dv is the same as du. There it is. And we're substituting u in for the denominator. So du over u. So if you're just seeing this for the first time, we didn't just do magic. I didn't just ignore the difficult stuff and so that we move on. I substituted. But like we substituted to get the new expression over here, a more simplified expression, we do need to substitute our bounds in. So if we put in 0 for v, then we'll see that the lower u bound is u is equal to 0 minus vt, or negative terminal velocity goes in that lower bound. If we substitute in v for v, then u is equal to v minus vt. All right, so the reason we substitute is to make the integration easier, but that does change our upper and lower bounds. On this side, it just remains the same. This is just a power rule. There's a t to the 0 power in here, and that's not going to be a problem. All right, I'm just going to start with the easier portion here for a moment. The integral negative k over m dt is just negative k over mt. And we're going to evaluate that in a moment from 0 to t. And the integral of du over u, like I indicated before, is a natural log of u. And we're going to evaluate that from negative vt to v minus vt. All right, time to evaluate. We plug this in. Start with my easier side here. T plugs into there, minus 0 plugged in there, so t minus 0. And likewise, ln of, remember the natural log, and you put these absolute bars there, v minus vt minus natural log of negative vt. Might look a little funky right now, but there's a way to simplify logs. There's a log identity. Log of x minus log of y is equal to log x divided by y. So natural log of v minus vt minus natural log of vt is equal to natural log of v minus vt over negative vt. And that's equal to negative k over m times time. So looking a little bit better, but if logs make you sick to your stomach, let's get rid of them. Just like multiplication and division are sort of like inverse operations. Have you ever considered taking the inverse sine of a sine of an angle, like inverse sine of sine theta, that's equal to theta? These kind of inverse functions and operations cancel each other out. So what we can do is raise e, the number e, to the natural log. Remember, those are involved. Natural log is log base e. So if we raise these two sides, e to the power of those two sides, that in essence cancels out that natural log. I know if you're a math person, I'm probably burning your ears right now. v minus vt. So kind of cancels it out there. Negative vt. Cancels it out in practice. Okay. Is equal to e to the negative k over m times time. And now we can start simplifying and cleaning this up. If you notice, this is it's an exponential function, and on our first page, that's sort of what these curves are indicating. There's some sort of exponential change here. So this is where we should be going. We should get a function out of this. When we analyze this function we just came up with for velocity, that looks like this curve. Let's check it out. All right. So algebraically, let's solve for velocity. What does v equal? Remember, this vt is a constant, the terminal velocity. It's the ending velocity. When we multiply on both sides, we end up with a v minus, or v equals, a negative vt e to the negative k over mt. And, this should be a v minus vt over here. We're left with this creature. and we're going to add vt to the other side. This becomes a velocity function of time, v of t. Add vt to the other side here equals terminal velocity minus terminal velocity times e to the negative k, it's a little backwards there, negative k over m t. And we can simplify in one more step to v of vt times 1, we're going to factor out the vt, 1 minus negative k over m t. And there it is, our velocity function. Booyah. Now, is this function looking like that thing we had on the first page? Well, let's check it out. Let's look at some limits here. When velocity is equal to 0, pardon me, when time is equal to 0, what is velocity? So if t equals 0, then that means this whole term up here is 0, and any number to the 0 power is 1. So when time equals 0, this parentheses becomes 1 minus 1, which is 0. So sure enough, our function does start at velocity of 0. How about when time becomes greater, greater and greater? As time increases, this is e to the power of negative. This is like a 1 divided by e to the t kind of a function. So as t becomes greater, the denominator becomes greater and greater and greater, meaning the whole number becomes less and less and less. So as t becomes greater, this term approaches 0. And if this term approaches 0, we're subtracting vt minus a number like 0. So our velocity becomes, over a long period of time, the terminal velocity. It's going to approach a maximum terminal velocity. So eventually, as t is very great, v of t becomes the terminal velocity. There it is. It agrees with our guess on the front page. Okay, that's the function right there. All right, now we got a few more creatures to work out. What is the acceleration and the displacement function going to be? And remember, to work these out, acceleration, how does it relate to velocity? Acceleration is the rate of change of velocity, it's the derivative. And velocity itself is the rate of change in position. Running out of room there. Okay, rate of change in position. So that's our relationships that are going to help us out. We're going to have to integrate to figure out displacement. We're going to have to take the derivative of this expression to come up with the acceleration. So let's do that. Start with a new page here. V of t equals vt. I'm going to spread this out again because when we take the derivative, it's a little easier to look at it in this form. E to the negative k over m times time. And now the acceleration is dv dt. So derivative of this. Derivative of a constant is 0. And got to take the derivative of this now. Now this is a coefficient in the front, so we got a vt. And what's the derivative of e to the x? Beautiful thing about e is the derivative of e to the x is e to the x. It's the same. The slope is the same as the function. So this is going to be e to the negative k over m t. But if you're moving along in your calculus class for the first time this semester, then you probably know something a little bit about the chain rule. So we take the derivative of something that's not just an x here, it's got a coefficient. We then have to multiply this result by the derivative of what's up there next to the t. The derivative of negative k over mt is negative k over m. Here's the chain rule. All right, now let's simplify. A of t function is, we got a negative times a negative is a positive, and we're left with a vt times k over m. Those are our coefficients, and e to the negative k over mt. Just does not want to go away there. It's still there. And that's it, but we can clean this up a little bit. Do you recall that vt is equal to mg over k? So the terminal velocity. And this looks like, what is that? That's trash in there. That's a bunch of junk, okay? But it's not really junk. It's important. However, if we substitute this back in as an mg over k, you'll notice that we've got a k over m multiplying right there. That term that won't go away, negative k over mt. And we're going to have some k's cancel and some m's cancel. And we're left with, surprise, surprise, acceleration due to gravity, e to the negative k over mt. There it is. Our acceleration function. What's that look like? If you plug in t at 0, what is a at 0? So if you plug in a 0 here, then we can get e to the 0 power, which is 1, and 1 times g is g, 9.8. So at time t equals 0, the acceleration is 9.8. And as t increases, what's that going to do to this term? It's going to decrease the term. So g is going to decrease, and as t approaches infinity, then a approaches 0. So it's going to decrease and approach, but never touch 0. And that's the same function that we got in our guess, the first page. So check, that one works. We got our v of t, we've got our a of t. Now for the one that's a little bit more involved, what about the displacement? V equals dy dt, which is, I'm going to rewrite this expression up top, vt e to the negative k over m times time. We're going to have to do another substitution rule here, warning, warning. So when we multiply both sides by dt, here's the time over here. There's no v's on this side. These are constant values, terminal velocities. So when we multiply both sides by dt, we get dy equals, parentheses, dt minus vt e to the negative k over m times time dt. And we're going to, since everything is good over here, we've got a dt and a t. There's no y's anywhere except for on the left. We're going to integrate from 0 to arbitrary time t later on. And we're going to start at the beginning at 0 position and fall down a distance y in our positive direction. So we integrate dy, there's a little y to the 0 power here, and it becomes y to the first. So we're going to put with a y minus 0, taking those bounds and plugging them in there. And over here, when we integrate vt, just the power rule for integration, we have a t to the 0 power becomes a vt times time. I'm going to go ahead and put in the evaluation bounds there, okay? And after that, all right, what is the integral of this creature times dt? I'm just going to rewrite this for now. So keep it as the integral. I have a negative, and I got a vt in there. E to the negative k over m t dt from 0 to t. Because I want to just focus on this one. Over here we're going to have a y equals terminal velocity times t minus 0 is just terminal velocity times t. So those are important to have in there. We'll come back to that. And what about this creature here? Well, to integrate this, we're also going to have to do a u substitution, just like the derivative of e to the x dx is equal to e to the x. The integral of e to the x is equal to e to the x plus c. So we need to get it to the form e to the power of u. And we're going to do another u substitution. U in this case is negative k over mt. So du is equal to negative k over m dt. And that means when we substitute into this expression, we need to solve for dt. That'll be equal to, in terms of du, equal to negative m over k du. All right, so multiply both sides by negative k over m to solve for dt. That's what we're doing there. So here's dt. We're going to substitute that in here and substitute negative k over mt for this. And we end up with vt, can't forget that, e to the u times dt, which is negative m over k du. Let's keep it going. Solve the integral. Oh, what about my bounds? I got to plug in a 0 for t. So when t equals 0, u equals 0. When t equals t, plug in a t, then u equals negative k over m t. And that's how we don't lose our time. Little expression here. Let me move this guy down here. Nope, it won't let me. All right. So just spread this out a little bit. Spread out the love. The integral of e to the u is e to the u. So we have to keep these creatures out here. Let's not forget about them. And the integral of e to the u is e to the u. And we're going to evaluate that from 0 to negative k over m t. Negative times a negative is a positive. So we're going to have a plus terminal velocity times m over k. And in here, we're going to have an e to the negative k over m t. Told you that won't go away. Minus e to the 0. We're plugging 0. That's a 1. Any number to the 0 power is 1. What I'm going to do is distribute this term here. Distribute. And write it out. We're nearing the end. I'm going to distribute to the 1 first. Okay, so distributed to that, that's why there's a negative there. We're going to add this distribution here. There it is. And that's it. You know, should we substitute in a terminal velocity like we did for the last one? Well, the terminal velocity is mg over k. So putting an mg over k here is just going to give us an m squared g over k squared. That doesn't make it any nicer. So this is actually probably the best form we can get. I guess we could try to work some kind of form of velocity in here, but I think that would just be a algebraic exercise. Let's not do that. So let's look at, is this the function that creates our expected displacement function? Well, let's look at it. Well, we have sort of like a line thing going on here. Do you see there's a like a y equals mx plus b type of thing going on here, where t is the x value and v is a slope. Now our b, this would be like a y-intercept over here. It's a constant. Notice it's in the negative, so it's like if we made a line, this line would sort of be like this, but kind of extend down and intercept in this negative y territory. Okay, so if we had a straight line here. So what about this? What is this creature here? At time t equals 0, what is the value of, this is not supposed to be a v, I'm sorry, it's supposed to be a y. Okay, y of t function. When t equals 0, e to the 0 power is 1. So what does y equal when t equals 0? Well, if this term is 1, then we're going to have a vt m over k minus vt m over k. At t equals 0, these two terms cancel one another out with subtraction. And we're left with just, plug in a 0 there. We're left with y equals 0. So our function actually starts here. And as t approaches a large amount, this e to the negative term here, this is going to make this whole term become less and less significant and approach 0. So after a long period of time, this term will disappear, and we're going to end up with a function that is essentially just that. So we're going to start with a 0, and it's going to transition into a straight line. We have our function, all right, our curve transitioning into a straight line. Isn't that beautiful? I just love that. But that's our nasty, ugly looking displacement function that turns from a quadratic into a straight line. There's our acceleration functions dependent on g, and our velocity. This is the main one you focus on with free fall, because it's really involving the terminal velocity of the object. Sometimes on an AP test, I've seen multiple choice questions pop up like with, here are 4 equations. Which one is the velocity equation for an object undergoing free fall? Undergoing air resistance, falling object undergoing air resistance. And I'll have you pick out this form. But just if you ever get to that and you're just like, oh, I don't remember all those, like, I didn't remember there's an e to the power or something, but look at the form, plug in a t equals 0 and a t equals big, and see which one works out the way it should. All right, we should start out with a 0 velocity and become a constant terminal velocity after that. But I have also seen this kind of scenario pop up on an FRQ, and I've seen it 2 or 3 times, 3 times I believe, so it's possible it'll come up. And what you'll need to do, most likely, because it just takes so long to solve and work through, they usually just ask for this step or a differential equation step. So you should be able to get to this point at least. However, that's really ugly. However, at this point in time, you don't just want to kind of get an idea for this, you want to learn it well. So what I highly recommend, and this will probably give you a nice warm fuzzy feeling inside when it works, but I promise you it is time consuming. So over the next couple of days, bring this out. Next 2 or 3 days, bring it out once a day. Start right now. Go through and recopy this process, recopy this step, the steps here. If you're not quite to that calculus level, you might want to save it until after you've gotten through integration. That might be more useful. But if you've done the calculus before, pull this out. Start with the force diagram. Something like this, where drag is not equal to weight, because that's really what we're looking at here. Write out the Newton's second law application. Get down to what v is in terms of mg over k, and note that, oh, if acceleration is 0, then you get this terminal velocity. Know how to do that part. Then rewind it a little bit. Substitute dv over dt for a. Work out the algebra to set it up. Set up the situation. And then solve it. Solve it yourself. Why is Shelley telling you to do this? Because if you do this once, twice, and then 3 times, by the 3rd or 4th time, I guarantee something's going to click in there. And you're going to be like, oh, I know how to do this. And that is that warm fuzzy feeling. You learn the process. You go through the problem solving. And that process is what allows you to learn what this is, how it works, and what the heck you're looking at instead of just chicken scratches that Shelley made on the screen. Right? It is good for you, and I really encourage you to do that in these next couple of steps. So take it out, try it. The first time you do it, you're just copying it down. The second time you do it, try to put it away and work it through as far as you can get. Look back at these notes if you need to after you get to that point if you get stuck. But after the 3rd time you do it, you might get most of the way through, or maybe all the way. And by the 4th time, you're going to have it. So it does take time out of your day, but it's well worth getting it. It is something that pops up on the AP test. It will be likely on your unit test in this class. And finally, at the end, do the graph interpretations as t equals 0, as t approaches a large value. Can you sketch out the graph by looking at the function? These are all very good, useful, helpful skills, not just in physics, but in math as you go forward. As you get into differential equations, this is the kind of stuff you're going to have to do. So it's well worth your time, well worth to take the time to get it now and to be a master at it later on. So I hope this video is very helpful to you, and I hope it wasn't too much of a drag. Bye.